Hello everyone, welcome to Unit 10 of online course on probability distributions. In previous modules, we have discussed probability density function of discrete random variable, especially discrete uniform random variable, Bernoulli random variable and binomial random variable. Now we are going to move on another important discrete random variable, that is Poisson random variable. In the case of Poisson distribution, we are discussing its relevance, important properties, characterization results and some applications of Poisson distribution in different fields. When we have defined the binomial distribution, we consider the situation as a random experiment in which outcomes are either success or failure. That is, we are concerned with both the happening as well as non-happening of the events. That is, happening we call it as success and non-happening we call it as failure. So, while discussing binomial distribution, we are concerned with both the happening and non-happening of events. But if we are concerned with and count only the happening of the event, we may use another distribution, and that is known as Poisson distribution to describe the model. So, when we are performing a random experiment and you count only the happening of certain event, we use Poisson distribution to describe the model. So, Poisson distribution is actually a probability model which can be used when the outcome of an experiment is a random variable taking on positive integer values 0, 1, 2, 3 etc. and where the only information available is a measurement of its average value. That is, while considering a random experiment, you count the number of outcomes occurred and the available information is its average value, the measurement of its average value. And usually we may discuss the Poisson distribution in two distinct ways. Firstly, as a distribution in its own right. This will enable us to apply statistical methods to a set of problems which cannot be solved using the binomial distribution. So, when we are applying binomial distribution, if it is not applicable to find the probabilities or if it is very difficult to find the probabilities, we can use another discrete distribution, that is Poisson distribution, to find the probabilities. Or secondly, Poisson distribution can be considered as an approximation to the binomial distribution, the binomial distribution with the parameters n and p. And the approximation is possible when the number of trials is very large. That is, suppose we are performing the experiment a large number of times and the probability of getting or probability of happening an event is very small. So, when n is large, that is number of trials is large and the probability of happening an event is small, then we can approximate the binomial distribution to the Poisson distribution. So, the Poisson distribution often provides a good model for the probability distribution of rare events that occur in any dimension such as space, time, volume or any other similar dimension. That is, suppose you are considering an event and that is very rarely occurring in any dimension in a particular space or particular time period or particular volume or any other similar dimensions. And suppose the information available is the average value of number of events is available to us. So, we can apply the Poisson model in that situation. Once again, the Poisson distribution can be applied in a situation like where the occurrence of events in any dimension such as space, time, volume, etc. are rarely occurring, and the information available is only regarding the average value of number of events occurred, and that is usually represented by lambda. And so, Poisson distribution occurs when there are events which do not occur as outcome of a definite number of trials. In the case of binomial distribution, we discussed the binomial distribution as the trials are repeated, trials are performed n times, and out of this n times, how many successes are obtained? That is our question while we discuss the binomial distribution. But in the case of Poisson distribution, the occurrence, the outcomes of a definite number of trials of an experiment, but which occur at random points of time, wherein our interest lies only in the number of occurrences of an event, not in non-occurrences. So, Poisson distribution occurs when there are events which do not occur as outcome of a definite number of trials of an experiment, but which occur at random points of time, wherein our interest lies only in the number of occurrences of an event and not in non-occurrences. But in the case of binomial distribution, we are interested in non-occurrences also, that is success and failure, occurrence and non-occurrence, success and failure. But in here, the Poisson distribution, we are interested only in the number of occurrences. And in several situations, we can apply Poisson distribution, and examples of random variable with the approximate Poisson distribution, include the number of house fires in a city on a given day. It is a rarely occurring outcome, and so if that is a situation, suppose you are counting the number of house fires in a city on a given day, then that can be modeled using Poisson distribution. It may be. And a number of telephone calls handled by a switchboard in a particular time interval, that can be modeled by Poisson distribution. Or traffic accident per day in a given location may be modeled by Poisson distribution. Number of radioactive particles that decay in a particular time period may be modeled by Poisson distribution. Number of errors a typist makes in typing a page may be modeled using Poisson distribution. Deaths due to rare disease can be modeled by Poisson distribution. So, these are the some situations where we can apply Poisson distribution, because in all these cases the occurrence is rarely, the event is rarely occurring, that is probability of getting that particular event is very small, and number of trials is very large. So, these are the examples where we can apply Poisson distribution. Now, come to the mathematical part of the Poisson distribution and how we can define the Poisson random variable. A random variable is defined as a Poisson random variable if, suppose, x is a discrete random variable, of course, a discrete random variable having the values 0, 1, 2, etc. So, these values with the probability mass function f of x is equal to e power minus lambda power x divided by x factorial, where x have the values 0, 1, 2, etc. already mentioned, and lambda is a positive quantity. Suppose we have a probability density mass function, probability density function of discrete random variable like this. We call this x as a Poisson random variable, and lambda is called the parameter of the distribution, and usually we represent that by x follows Poisson with the parameter lambda. So, this is our definition. Random variable x taking the values 0, 1, 2, 3 etc. is said to follows Poisson distribution with the parameter lambda if probability of x is equal to x is this expression, this value. And lambda is called the parameter of the distribution. And also you note one thing, see e power minus lambda, lambda power x divided by x factorial, x is equal to 0 to infinity, and that is equal to e power minus lambda sigma x is equal to 0 to infinity lambda power x divided by x factorial, and that is a non-infinite series, and the value is equal to e power lambda, and so that is equal to e power 0 is equal to 1. So, this is a non-result for us because the sum of the probability mass function is equal to 1, and that can be established using the non-infinite series sigma x is equal to 0 to infinity lambda power x divided by x factor is equal to e power lambda. And as I mentioned already, this Poisson random variable can be considered as a, or Poisson distribution can be considered as a approximation of the binomial random variable, and the cases the binomial parameter n, binomial parameter value n is large and p is small, the binomial random variable can be approximated to Poisson random variable. That is, when the number of, in the case of binomial random variable with the parameter n and p, suppose we have a binomial random variable with the parameter n and p, and you know the n is number of trials, n is actually the number of trials we performed, and p is the probability of getting success. In the case of binomial random variable, we have these parameters, n and p parameters are these are the concept behind the parameters. N is the number of trials and p is the probability of getting success. Suppose we are considering the situation, number of trials is very large, that is n tends to infinity, and second case, probability of getting success p is very small, that is p tends to 0, that is probability of getting success, that is this is a success or the event is very rarely occurring, then only the probability is very small. So, probability of success p is very small, and of course, the product between these two numbers n and p, that we call it as lambda, is a finite number. So, if we are applying these three conditions, that is number of trials n is very large and probability of getting success, that is p is very small, and if lambda p is equal to np is equal to lambda, a finite number, then the binomial distribution is the probability function or probability mass function of Poisson random variable. So, we can prove this result, that is the approximation of binomial distribution to Poisson random variable under these conditions, and that can be established. Suppose x follows binomial with parameter n and p, and just consider the probability mass function ncx p power x, and of course q, that is q is we know 1 minus p or power n minus x, and the conditions we are applying here, one, the n tends to infinity. The first condition we are applying here, n tends to infinity. And second condition we have p tends to 0. And third condition we have np is equal to lambda. Or of course, np is equal to lambda means p is equal to lambda divided by n. Suppose we are modifying this expression, and let me write this as n factorial divided by n minus x factorial and p as lambda divided by n power x and 1 minus 1 minus p, that is lambda divided by n all power n minus x. So, that is you apply the third condition in the binomial probability mass function, we can reduce the expression to this form. Again, this is simplified to n into n minus 1 into n minus 2 etc. n minus x minus 1 divided by x factorial lambda divided by n power x 1 minus lambda divided by n or power n minus x. So, that is by cancelling the common factors with n factorial and n minus x factorial, you will get the result. Okay. So, that is this is the result, n into n minus 1 into n minus x plus 1 lambda power divided by okay. And before that, I think this is the factor we have, n into n minus 1 into n minus x plus 1 divided by x factorial and lambda by n all power x 1 minus lambda divided by n all power n minus x, that we have established. So, okay, this is the last expression we have. And then what we are doing here, this is equal to n into n minus 1 into n minus x plus 1 divided by n power x. See, earlier we have lambda power x divided by n power x, and this can be written as one minus lambda divided by n or power n minus x. Okay. Again, this is n into n minus 1 etc. up to n minus x plus 1 divided by this way also we can write. This is 1 minus lambda divided by n all power n approximately equal to e power minus lambda, and as I mentioned n into n minus 1 n minus x plus 1 divided by n power x approximately equal to 1. This is not approximately, this is equal to 1, and 1 minus lambda power n power x is approximately equal to 1, because we are applying n tends to infinity here. When n tends to infinity, this factor become e power minus lambda, and when n tends to infinity, this become 1, and this when n tends to infinity, this become 1 minus 0, and so on. Substituting the quantities, we have this expression become, this is becoming 1, and this is e power minus lambda, and this is already established as 1, and this x factorial. So, that is the function value f of x is equal to e power minus lambda, lambda power x divided by x factorial. So, once again I repeat, if the number of trials n is large and p is very small, we are simplifying the expression of binomial distribution and applying these conditions there, that function value is approximately equal to e power minus lambda, lambda power x divided by x factorial, where x is equal to 0, 1, 2, etc., and lambda greater than 0. That means Poisson distribution can be considered as a limiting case of the binomial distribution when these conditions are applied. So, and some examples of where we are applying the Poisson distribution in order to calculate the probabilities are now we are going to discuss here some examples. Suppose you consider number of accidents occurring in a highway each day is a Poisson random variable with the parameter lambda. Here the parameter lambda means the average number actually. Then the probability that no accident occur in a day is given by. So, that is it is a Poisson random variable. We are having the event as accidents occurring in a highway, and that is considered as a Poisson random variable, and so and the parameter lambda is given as 3. If it is, the question is what is the probability that no accident occur in that day in that particular region, particular area. That is by obtained by probability that x is equal to 0, e power minus lambda, lambda power x divided by x factorial, that is our probability mass function, and x is equal to 0 means this become e power minus lambda alone, and that is e power minus 3, and that is approximately 0.633. So, that is when we have a situation of identifying the accidents occurring in a highway, and suppose you are modeling that event using the Poisson distribution, and with the we have a prior information regarding the average number of occurrence of accidents per day is lambda is equal to 3, and if it is the Poisson using the Poisson probability model, you can find the probability of no accident occur in a particular day in that region, in that area is e power minus 3, approximately 0.633. Similarly, another example, suppose box containing 200 items, and find the probability that at most one defective item will be found in a box of 200 items if experiment shows that 2% of such items are defective. So, note that here the 200 items. So, you are given there are 200 items, and experience shows that 2% of such items are defective. So, that means probability of getting a defective item, from the previous knowledge we have, it is 2%. So, that means 0.02. So, this is a model, this is a situation where we can apply the Poisson distribution, because see here number of items is 200. So, that may be considered as a large number, and the probability of getting a defective item, it is 2%, that is 0.02, that may be considered as a small number. So, n is large and p is small here. So, you can approximate this experiment using the Poisson distribution. You can model this experiment using the Poisson model. And so, if it is, you just find what is NP, that is our lambda, and that is equal to, lambda is equal to this value. And so, our question is, find the probability, if experiments of such items are defective, find the probability that at most one defective item. At most one defective item means x less than or equal to 1, at most one defective item. That is probability of x is equal to 0 or x is equal to 1. That is probability of x is equal to 0 plus probability of x is equal to 1. And this is equal to, since we are using the Poisson probability model, f of x is given by, or probability of x is equal to x is given by e power minus lambda, lambda power x divided by x factorial. This is our Poisson probability mass function. You just write the value of probability of x is equal to 0, this is e power minus lambda plus probability of x is equal to 1, that is e power minus lambda into lambda power 1 divided by 1 factorial, and just substitute lambda value. Already we calculate lambda is equal to 4. So, this is e power minus 4 plus e power minus 4 into 4, or we can have, the value 5 into e power minus 4. So, this is an example where we are applying the Poisson probability model because the number of trials is large and p is small. So, if it is, the probability value is equal to probability of the required probability, that is at most one defective item is obtained out of 200 items, of which the probability of getting a defective is given to you, and because the probability of getting a defective is given and 200 items are there, while using the Poisson distribution, you multiply those two values and find the lambda, because lambda is equal to NP, and this is the way we can calculate the binomial Poisson probability value. You can use the binomial distribution here also to find the probability values, but Poisson model is simple to calculate the probability values rather than the binomial distribution. And another example, you consider a situation if 1.5% of animals are suffering from a rare disease. Find the probability that out of 200 animals in a region, at least 2 animals are suffering the disease. No animal is suffering from the rare disease. So, if this is the situation, here also just look, here 1.5% animals are suffering from a rare disease, and the total animals we are considering 200. So, here n is equal to 200, n is equal to 200, and the probability of suffering from a rare disease is given to you, that is 1.5%, 1.5%. So, this is the value. Okay. So, p is given to you, and this is, so using the Poisson approximation, we can have the NP value, and that is our lambda value, that is 200 into 1.5 divided by 100, or that is 3. So, using the Poisson approximation for this particular example, we have lambda value is obtained from the given values of, that is number of animals is 200, and probability of suffering from a rare disease by an animal is 1.5% probability, that is 1.5 divided by 100. So, the lambda is equal to 3. If it is all the probability values, whatever be the required probability, you can find, that is using the probability mass function value. Probability mass function value here, f of x is equal to e power minus lambda, lambda power x divided by x factorial, and lambda is we obtained as 3. So, e power minus 3, 3 power x divided by x factorial, where x is equal to 0, 1, 2, etc. This is our probability mass function. Now, just look what are the required probability values. The first one, at least 2 animals are suffering from the rare disease, at least. So, that means at least 2 animals are suffering from this one, or that is 1 minus probability of x less than 2. That is 1 minus probability of x is equal to 0 or x is equal to 1. And substituting the values, we have probability of record probability is this one. This is 1 minus probability of x is equal to 0. See, we have the lambda is equal to 3. Okay, lambda is equal to 3. So, e power minus 3 plus e power minus 3. So, this is the probability of the record probability, that is probability that at least 2 animals are suffering from the rare disease is obtained by 1 minus probability of x is equal to 0 plus probability of x is equal to 1, and that is 1 minus e power minus 3 plus e power minus 3 into 3, or this can be simplified as 4 into e power minus 3. So, this is the probability. And again next step, the question is about no animal is suffering from rare disease. No animal suffering from rare disease means x is equal to 0, that is no animal suffering from the disease, that is x is equal to 0, that is e power minus 3. So, whatever be the probability values required corresponding to this type of questions, we can calculate the values using the Poisson probability mass function if lambda value is available. And lambda value is available either if we have the information on average number of occurrence of the events, or if we have the information on total number of trials and probability of getting an event. That is, if lambda is available directly, that is average number of occurrence, or if the n number of trials and p probability of occurrence of the event. So, if these two are available using the Poisson approximation, you can find lambda is equal to np, or if lambda is available directly, then we can find the probability values directly. So, wherever we can apply the Poisson probability model whenever we have the situation, that is number of trials is very large and occurrence of certain event is rarely occurring, and such a situation we can find the probability values using Poisson probability mass function. So, thank you for listening this module. Thank you.